Hey guys, this is going out by request. Chapter 12, number 29, GPS satellites, GPS, global positioning system. Satellites orbit at an altitude of 2.0 times 10 to the 7th meters. I assume that's above the surface of the Earth. So, A, find the orbital period, and B, the orbital speed of such a satellite. So the orbital period is the time it takes to go around once, and the orbital speed is its velocity at that altitude. So let's see what we can do. Welcome to Paintbrush, the cheapest of the cheap. Somewhere around here I've got a pen. Let's see if this works. Check. So question. T equals question mark, I guess seconds, we'll figure that out. That'll be the period. And then the second question is the orbital velocity equals question mark. I'll do end it up in kilometers per second, because that's, when you're talking about these velocities, it's just makes more sense to report your answer in kilometers per second. Now for this one, I'm going to draw a little picture as best as I can. Let's see if I can do this. I want to do a circle. Look at that, a little circle. What a little cutie. So that's the Earth, and then up here somewhere is our satellite. And I assume it's got satellite wings, yada, yada, yada. Okay, so the information that was given in the book, that there is the altitude, and then that, I'm going to call that, what did I end up calling that? I'll just call it the altitude. The altitude equals 2.0 times 10 to the 7th meters. So that's that right there. Now, tricky. I have to actually know this information as well. It's the center of the Earth. I need to know not just the altitude of the satellite, but I need to know this total distance here from the center of the Earth to the satellite up in space above the Earth, perfectly executed straight line. I need to know that. Right there. So what I had to figure out first in the back of the book, I looked up the radius of the Earth, and the radius of the Earth is 6.37 times 10 to the 6th meters, and I'm going to do it in meters for now, even though I'm going to end up in kilometers per second for some of these numbers. I'm going to do it in meters, and you'll see why in a minute when it comes to making sure my units cancel out. So then what I said, the next thing I'd said is I said the radius of the GPS, oops, the radius of the GPS, which is this one, that is equal, well, you just add those together. I took my 10 to the 6th and made it 10 to the 7th, and it was 0.637 times 10 to the 7th, and you can just add these in your head. It's 2.637, sorry, Control Z, 2.637 times 10 to the 7th meters. That's the total distance from the center of the Earth to the GPS satellite. Now what do I do? I'm doing this period problem first. That's my thing. Oh boy, ready for some math? Kepler, Johannes Kepler, was a scientist that figured out 3 laws, and Kepler's third law goes a little something like this. The orbital period of a satellite is proportional to the cube square root of the radius. So it just like if you just put like the orbital graph, the orbital period to the cube, the square root of the cube of the radius, you would get a straight line for all the planets in the solar system. Well, that's going to work for this too. This works for the solar system with the sun at the center, but it'll work for a GPS satellite in orbit around the Earth as well. And there's a funky-dunky little equation that looks something like this. The orbital period is equal to 2 pi big G. Do not confuse big G with little g. Big G is the, I'm screwing this up. Let me backtrack here. The equation is this. The orbital period is equal to 2 pi divided by the square root of big G and the mass of the central body, which in this case is the Earth, times this whole thing. This equation's in the book, is where I got it, times the square root of the cube of the radius. Now, I could bore you to death. I did it, and I could bore you to death with the units and how the units work out. This is the gravitational constant. It's the force of gravity acting between two 1 kilogram objects separated by 1 meter. And I guess rather than grind out all the units, you'll just have to trust me on this one, or at least prove me wrong if you can. I'm going to get an answer that's in seconds if I crunch all these numbers, and it's like 2 pi, check, and then this is 6.67 times 10 to the negative 11th Newton, check, meters squared per kilograms squared times the mass of the Earth, which I found to be 5.97 times 10 to the 24th kilograms. And then this whole thing is square rooted down here. Yeah, and then this is also times, this is getting wanky, 2.637 times 10 to the sevenths, and then this is like cubed and then square rooted. Now, I did it. If you do all of this stuff here, you're going to get an answer that's in seconds. Prove me wrong. I did the math. You should too. I got 42655 seconds. That was the number I got. And if you convert that into hours, you get 11.9 hours. And that's the answer in the back of the book. So I'm doing something right. And I do get an answer that's in seconds, but for the sake of brevity, I will not show you how that all works out. But anyways, that's how I did that one. Really tricky math. Order of operations are really important, especially with this square root of the cube situation. But that's why we teach you algebra, so that you guys can understand physics. There you go. The next thing has to do with the orbital velocity, and there's two ways to do this one. There's an equation in the book. There's a section of the book that talks about escape velocity, and it says that the escape velocity is equal to the square root of 2 g, which is the big universal gravitational constant, times the mass of the central body, which in this case is the Earth, and divided by, for us, the radius of the orbit, which is the GPS radius that I talked about above. Now, this is the escape velocity. Kind of tricky, but if you look at some of the equations in the book, and if you do a little bit of research, you'll actually figure out that's escape velocity. How fast would this satellite have to go at that altitude to leave the Earth's gravitational influence and never come back? That would be like an asymptotic orbit. The thing would just take off, and its zenith would be at infinity. It would just keep going. But that's not what we're talking about. We're talking about the orbital velocity at that altitude. And it's got to do with just removing that factor of a 2 and plugging in these numbers. Mass of the Earth, the radius of the GPS satellite. I showed you all these numbers up above. But if you do the math, you get, how'd I do? 3.886 meters per second, which is about 3.9 kilometers per second. And that checks out. So that's the orbital velocity at that altitude. Which is, does that answer make sense? Yeah, that's wicked fast. Now, another way that I could do this is I thought about it in terms of, well, let me take the circumference of the circle of the orbit. So let's say that I have a circle. This satellite's going to be whipping around in a circular orbit, and I know the radius of that circle. It's this GPS radius that I showed you. So what I can say is, well, 2 pi r, that's the GPS radius of the GPS satellite's orbit. And then over the time, which we just figured out, which is the orbital period. And I could say that that is equal to 2 pi times the radius divided by the time. And I got, rather than write down all these numbers because that gets kind of boring, I got 3.884 meters per second, which is 3.9 kilometers per second, which checks out. So I did it both ways to make sure I'm doing it right. So there you go. That's how you crack that apple. Don't forget to slap like. If you guys have any questions, make sure you send them to me, and enjoy the rest of your day.